All right, good morning. So we're going to do series circuits, or the second lesson to do with circuits. So previously we just learned that if you have a battery, you can connect it to a light bulb. And really that's the same as a circuit if I drew it like this, where that symbol means resistor, that means battery, and if you remember, it always goes from positive to negative, going around that way. We have a resistor there and a battery there. Here we have a battery and we also have a resistor, but this is the symbol they write for a light bulb. So we have a battery going to a light bulb and back to the battery. And it'll only be on if it's a closed circuit, which means it connects back to the battery. So again, it goes positive to negative. So now we go to the first question. What is a series circuit? So a series circuit is a circuit with multiple resistors, one after the other. So an example is this picture here. We have a battery here, and it goes up to one resistor, goes through it, keeps going, goes to a second resistor, goes through it, and then goes to a third resistor, goes through it, and back to the battery. So essentially what's happening is you have a certain voltage here, so like a 1.5 volt battery. Let's see if I have one here to show you. So an example like this, you have a 1.5 volt battery, and then it goes away, and these three resistors are going to take some of the voltage away from this battery so that when the electrons go all the way around, they'll have zero potential energy once they hit here. Okay, so what's going to happen is that it's going to have 1.5 volts, it's going to go, and then this resistor is going to take some of it, so maybe it'll have 1 volt, and then this resistor is going to take some of it, let's say it has half a volt left, and then this resistor is going to take that last half a volt, and then it's going to be 0 when it reaches there. Okay, so what they say is when they go through resistor, the voltage drops through each resistor. Okay, so the voltage drops, or the pressure drops through each resistor. Okay, so let's do a warm-up based on last day. What is the resistance of a light bulb if there are 3 amps? Remember, amps is current, okay, the amount of charge per second. It's the current of the stream of 3 amps going through it from a 12 volt power outlet. So let's draw it first. We got a battery, and then we go, and there's a resistor, and back to the battery. Okay, I'm going to make positive up there, negative there, so it's going that way. So we know the current I is equal to 3 amps, and we know the power from the battery is 12 volts, so I'm going to put that there. So what is the resistance of a light bulb if there are 3 amps going through it? Okay, so we have V equals IR, and we want to know what the resistance of this resistor here is. So I'm going to call it just R1, and I'll put a 1 there. Just say I'm talking about that one. So here we want to find out what the resistance is, so I'm going to solve for R, divide by I, so it'll be V over I. Okay, now we can put our values in. Our our voltage is 12 volts from the battery, so it's probably a car battery, and 3 amps, which is quite a bit, 3 amps of current going through it. So overall I have 4 as my answer, 12 divided by 3, and then the unit for resistance, if we remember, is ohms. So 4 ohms of resistance will go through this resistor. And what will happen is there's 3 amps of current, so it'll go a certain speed, 3 amps, whatever that is, and it'll go, and the pressure drops by 12 volts when it hits this resistor. So it's going to go from 12 volts, hit this, and then be at 0 volts. Okay. If you want to be really technical, in real life, what really happens is the wire has a certain resistance, then you have a resistor, and then you have another wire which has another resistance. So essentially everything has resistance. So theoretically, if I were to really draw this, I would draw a little resistor, and then we'd have our resistor, and then a little resistor again. So everything has resistance. So in reality, it's not just 12 volts being dropped there, it's really a little tiny bit being dropped through the wire, and then maybe 11.5 volts being dropped, and then a little bit of volts being dropped again. So that's what really happens. Alright, so now it says let's try this with 2 light bulbs. But first of all, let's see if I have an example of that first warm-up for you. So here I have a little bit of a circuit. So I got a battery, and it's connected through this white wire to this light bulb, and then it's connected through the black wire to this switch. If I close this metal thing, it'll close the circuit. Right now it's open, and then this red one goes back to the battery. Okay, so I'm going to get the battery out of the way just so we can see. You have your switch. So if I take this and I close it, you can see the light turns on. Okay, so the light bulb turns on. So my battery was 1.5 volts. So if I take this, which is a multimeter, you can turn, and there's certain settings you can do, but if we want to see what the volts are of this that are going through this light bulb, I can turn, and that one's probably going to be the easiest one for us to read. It means it goes up to 20 volts. Okay, so let's see how many volts are going through this light bulb right now. So I'm going to take this and touch it, and touch the other end, and it'll essentially tell you the voltage that's being dropped. I guess you have to see what it says. So we have 1.13 volts of that 1.5 volt battery is being dropped through this light bulb. Okay, so that is how much volts that this light bulb is dropping right now, and that's essentially how bright it makes it, 1.13 volts. You can bet if I had more volts being dropped, it would have a stronger light. Now let's try amps. If I go here, I can go to this here, saying say it goes to 200 milliamps. Okay, so whatever it reads here will be in milliamps, which means you need 1,000 of them to reach 1 amp. Okay, so this goes to 200 milliamps. So when it comes to amps, you actually have to take it off, and you have to connect it in circuit. So I have to touch it there, and I have to connect it to this one here like it was in circuit. So you can see that this circuit, you can see when I touch it, the light bulb actually does go on a little bit, but it's saying we have almost 90 milliamps of current, which is 0.09 amps. Okay, so there's just 2 examples. Or an example of a circuit here. I have 0.09 amps going through, and the voltage drop is around, I can't quite remember, but 1.2, I think, volts. Alright, so we had that circuit there. Now it says, now let's try it with 2 light bulbs. Let's draw that. So I have a little thing here. 1, 2. I didn't draw the lamp symbol, but you can imagine those as 2 light bulbs. Okay, now draw a circuit with 2 light bulbs. Well, I did that. One's going to have 4 ohms, and the other one's going to have 4 ohms of resistance, because in this last example we had 4 ohms was our light bulb. Okay, so this one's going to have 4 ohms, that one's going to have 4 ohms, and then our battery's still 12 volts like the last example. So there we go, we drew that. So now let's go to this question. If the battery, 12 volts, has 2 light bulbs, which is 4 ohms each, what is the overall resistance? Well, we know the overall resistance is, since it's a series circuit, what you end up doing is you just add up the resistances. So there's 4 ohms there and 4 ohms there. Our overall resistance is 8 ohms of resistance. Pretty easy. Now it says, what is the overall current? Okay, last time our current was 3 amps here. Is it the same when you have 2 batteries? It turns out no. So our current now, we have to use our equation V equals IR, but whenever you're using, trying to find current of a series circuit or any circuit really, you need to do overall resistance, which is called equivalent resistance. Overall resistance is called equivalent resistance, and we put a little EQ. So our voltage of our battery is equal to our current of the whole circuit times the equivalent resistance. So if we want to find out our equivalent resistance, or I mean our current, it's I equals V over R EQ. So our voltage here is going to be 12 volts, and our overall resistance, if you remember, was just 4 plus 4, 8 ohms. So overall our current is going to be 12 divided by 8, which is 1.5. And since it's current, it's amps. So if we look, adding another light bulb actually decreased the current in the circuit, 1.5 amps. Okay. So overall, this one had a 12 volt drop and its current was 3 amps. Here we have a 1.5 amp current, so half is quick. And the amount that's being dropped, let's look. Voltage drop on one light bulb. Let's see if we can calculate that. Everything in this unit we have to use the V equals IR. But since we're only dealing with one light bulb, we're no longer needing the REQ. We don't need to look at the whole circuit's equivalent resistance. To find the current, you do. But here, if we're just looking at one, we just want R1, say. So our voltage overall that we're using is going to be, or we need to find that. So our current is 1.5 amps. Is how much current is in the whole circuit. That's one thing to note. Is current going in a series circuit does not change. So current in one spot is the same as current there. It's the same there. Okay. So 1.5 amps of current. Our resistance we found out for one light bulb is not 8, but it's 4. And that gives us a voltage drop through that one light bulb as 1.5 times 4. And that gives us 6 volts of current dropping through that light bulb, which makes sense because they're the same ohm resistor. So as it goes, half of it gets dropped there and half of it gets dropped there, and then it's 0 by the end. Okay, so our voltage in this circuit is 6 volts with 1.5 amps. So you can see that in our one example, having that one lamp or light bulb had 3 amps of current and 12 volts of potential, electric potential. And this one, each light bulb goes 1.5 amps of current and only gets 6 volts of electric potential. So essentially half the current, half the electric potential if you add another light bulb. Okay, let's look at our circuit here. So again, I have the same battery. What I'm going to do is I'm going to disconnect this switch, get rid of it, and I'm going to grab another one. So I still have the other one. Right now it goes from the battery through the white cable here, and then through the black cable here, and then through the red cable back to the battery. So when I connect this, it should be a closed circuit. Let's see. And look at that. You can barely see it. It's a less strong light than before, but now I'm lighting 2 of them. So this is a series circuit. It goes through this one and then through this one and through the wires as well. So if you remember, technically each wire has a tiny bit of resistance, but our 2 ones we're really worrying about are the resistance of each of these light bulbs because they're a lot higher. So we have 1.5 volts coming from this battery through these two light bulbs. Before there was around 1.2 volts going through each light bulb, and now if I change it, I can see I'm going to look at, this is in the units milliamps, or millivolts, sorry, which means whatever reading it has, you have to divide by 1,000, and that's how many amps there are. Okay, so it says 595 volts, but it's really millivolts. So divide by 1,000, or just move the decimal place 3 times, and it's 0.59 volts going through this battery. Now let's check the other one. Not battery, light bulb. It's kind of hard to touch them sometimes. And this one has 600 or 0.68 volts going through it. So 0.68, and this one was what again? .59. So you can assume, since this one had more of a voltage drop and this one had less of a voltage drop, this one had, let's see, more resistance. Yeah, this one had more resistance then to take up more of the volts. This one had less resistance, that's why it was a bit different. So you can see that not every light bulb is made the same. Okay, so that was me just trying to show you an actual circuit. So let's finish up these questions. We have equivalent resistance equation of a series. So this is a series circuit only. We'll get into parallel circuits. If you look at the bottom here, we have a series circuit where you go through all 3, or a parallel circuit where it kind of branches off. But we're doing that tomorrow. So just series circuits today is this equation here. The equivalent resistance, or the overall resistance of the whole circuit, is just the resistance of all 3 resistors, or all how many there are resistors added together. So in our circuit would be kind of a wire plus a light bulb plus a wire would give us the one with only one light bulb. Okay? All right. So we're almost through here. For the last example, it would be Req is 4 ohms plus 4 ohms would give us 8 ohms. You just add it together. Nice and easy. So it says now 4 loads are connected in series to a 12-volt battery, and they all have different resistances. So it's not just an easy division, but we can draw our circuit. So I'm going to draw one here, I'm going to draw another one there, I'm going to draw another one here, and then I'll draw another one there. So now I'm going to call this R1, R2, R3, R4, just to make it easy to denote. Our current's going to go that way. And I'm going to also write the resistances: 3 ohms, 5 ohms, 7 ohms, and 9 ohms down there. All right, so I drew my circuit. That's always the first step. Almost 12 volts got to add there as our battery. Draw and find the equivalent resistance of the circuit. We know Req is just R1 plus R2 plus R3 plus R4. All the resistors added together. And what this is going to be is just 3 plus 5 plus 7 plus 9. So that's 8, 15, 24 ohms. So 24 ohms of resistance in this whole series circuit. And that's the equivalent resistance. And once you find this value, you can then find how many amps are going through the circuit. Okay, because the amps directly is related to the whole circuit. Okay, if I got rid of a resistor, the amps value would change. So let's go here, the total current in the circuit. We use our V equals IR with our little EQ down there. So if we want our total current, which is going to be our current everywhere in the circuit, it's just going to be I is V over Req. And our volts here is from our battery. It's going to be 12 volts. And our Req is going to be our 24. So overall in this circuit here, we have a 12-volt battery and all these resistors. The current has to be half an amp. Okay? Half an amp, which is fairly small. And then we got to do our last question, the potential difference across the 7 ohm load. So it just wants the voltage drop, because potential difference just means voltage drop through just this resistor. So how much does it drop through this one? Well, you can calculate it using the same old equation, V equals IR, because we know what the current is now, half an amp. Since we find half an amp for the overall, it means it's going to be half an amp through everywhere. Okay, in a series, that's how it works. And then R, this time it's not REQ, it's actually R of 3. It's just the resistance of our third one, because that's what we're trying to find. So that's 7 ohms, and then that means our voltage is going to be 7 times half, or 3.5 volts through our third resistor. Okay, so that one drops 3.5 volts. 3.5 volts of the 12 volts. Okay. So you'll assume, since this resistance is more, that this one is going to be more than 3.5 volts, and these two are less, so they're going to be less than 3.5 volts. Okay, so that's the lesson on series circuit. Good luck with the questions. They're a little difficult, but it's an interesting topic nonetheless.